This is the explanation for Trial 1 of the Unit 3 lab. So for this lab we had a car on an inclined plane with two photogates set up, a photogate A and a photogate B, and we were looking to calculate the acceleration on the ramp with three different methods. The first would be using the photogates to calculate velocities and use a distance to find acceleration. The second would be to use the mass of the car and the angle of the ramp to find the component vectors of the weight, which we could then compare to the other forces present to calculate the acceleration. And the third was to calculate the acceleration purely based on the angle of the ramp. So this first setup right here deals with the photogates. We had photogate A time. So when we released the car passed through photogate A, and the 5 centimeter flag of the car interrupted photogate A for 0.1032 seconds. The car then traveled 50 centimeters or 0.5 meters, and then the 5 centimeter flag interrupted photogate B for 0.0431 seconds. It makes sense that B is a shorter time than A because it was traveling faster at B because it was accelerating. So here's the data for our first trial. Photogate A time, photogate B time, a flag length which we converted to meters, and a distance between the gates which we converted to meters as well. Now to calculate the velocity at each gate, we're going to use the basic velocity is distance over time formula, with the distance being the flag length and the time being the photogate time. What this will do is it will take a flag that is technically accelerating through the gate, and it will average the initial velocity of the car when it trips the gate and the final velocity when it leaves the gate, and you'll actually end up getting a velocity right in the middle of the flag. And this will happen for both gates. So to find the velocity at gate A, we do the flag length over the photogate A time, and that gave us a velocity of 0.48 meters per second. To find the velocity at photogate B, we did the flag length again over the photogate time, which gave us a velocity of 1.16 meters per second. It's nice that it's accelerating. It's going from a slower velocity to a faster velocity over a distance of 0.5 meters. We then took these velocities and plugged them into the time-independent motion formula, where we have Vf squared minus Vi squared equals 2AD. And we know that Vf was our second velocity, or our B velocity. We know that Vi was our initial velocity, or our A velocity. So by plugging those two velocities that we calculated in along with our distance between the gates, we find an acceleration of the car to be 1.12 meters per second squared. This is the acceleration that we actually had in the lab. Now remember, this lab was done at a 10-degree angle, so it's not much of an acceleration compared to the 9.8. 1.12 isn't much compared to 9.8. But this is the actual acceleration of the car, the one that really happened in front of us. Next, we're going to look at how forces come into play with calculating acceleration. The second method we used was using the components of the weight vector. Now in this one, we're actually neglecting friction. We're going to look at what the acceleration should be of the car without friction based on the angle of the ramp and the mass of the car. Now if you remember, when we angle a ramp, we're no longer dealing with an x and y axis. Our x-axis now becomes a parallel axis, and our y-axis becomes a perpendicular axis. So that's where we get the parallel and perpendicular symbols from, as indicated here and here. So the mass of the car, we placed it on a scale. We found the mass to be 345.35 grams, which we converted to kilograms. And then by using this mass and the acceleration due to gravity, we can calculate the weight of the car by using W equals mg, and we can calculate it to be 3.38 newtons. Now that is the weight vector going down right here. By using the parallelogram rule, we can make a line to the perpendicular line and a line to the parallel line and find these two components, a parallel and a perpendicular component of the weight at 10 degrees. Now this perpendicular component is serving the role of holding the car on the ramp. So the car is not going through the ramp, and it's not flying off the ramp. It's holding it on the ramp. The parallel component is responsible for moving the car down the ramp at an acceleration. So if you look at the weight, if you tilt your head to the left, you can see that the weight is heading into the ramp and to the left of the ramp. So the weight is doing two things here. To calculate these, we're going to break this back up into its triangle, where we have the perpendicular component here, the parallel component here, and the weight is the hypotenuse of the triangle. So the perpendicular component is adjacent to the weight, so we use cosine. So perpendicular equals weight times the cosine of the angle, and that gives us a perpendicular component of 3.329 newtons. We do sine for the opposite side, which is the parallel component, and that gives us 0.587 newtons. Now, it's reasonable that the parallel component is so small compared to the perpendicular component because the angle is only 10 degrees. If it was 0 degrees, there would be no parallel component, so it's a very small part of the weight that's actually moving this car down the ramp. So in this example, we know that the perpendicular component is opposing the normal force. The perpendicular component of the weight is pushing the car into the ramp. The normal force is supporting it out of the ramp. So those two are equal to each other, equal and opposite. The parallel component is then the only leftover remaining part of any force that's responsible. Remember, there's only really two forces here, the weight and the normal force. The parallel component is part of the weight, and that is the part that is the net force that's responsible for acceleration. So if you do the net force equals mass times acceleration, with that parallel component and the mass of the car, which we calculated up here, you can find the acceleration of the car as 1.7 meters per second squared. Now this is what the acceleration should be without friction, if there was no friction present. We're now going to take a look at the theoretical formula for acceleration on an incline to see which of these two methods is the most accurate. Okay, using the acceleration formula, a equals 9.8 sine theta, this is the formula that we use for any angle in relation to gravity's acceleration downward. On a ramp, doesn't matter, any angle, if you're falling towards the ground, whatever, as long as you're at an angle towards the direction of gravity. So in this case, we do have an angle of 10 degrees, and that is made with our weight. So if we do 9.8 sine of 10 degrees, we get 1.7 meters per second squared, which is the same as the acceleration we had from the component of the weight. Now, our actual acceleration was 1.12 meters per second squared. So why is that different from the theoretical acceleration of what it should be and the acceleration over on the other side from what the forces provide? Well, the reason is this formula and the component of weight that we saw in the last one, those two don't deal with friction. They don't take friction into account. In reality, there's three forces acting here. There's weight downward, normal force 90 degrees to the surface supporting, and friction acting opposite the direction of motion. That friction force is going to take away from some of that parallel component. So we need to calculate that. If we use the acceleration that we actually got from the photogates and multiply it by the mass, we get what the real net force is. Now the net force without friction was 0.587 newtons. The net force with friction, which uses the acceleration that we had, is 0.387 newtons. That's a difference of 0.2 newtons of friction. So in reality, there was 0.2 newtons of friction acting against motion and 0.587 newtons of parallel component. When you add them together, you get 0.387 newtons responsible for the acceleration, which is 1.12 meters per second squared. So this is the trial for 10 degrees. We then adjusted the angle to 41.5 degrees and collected data, which you should have in your notebook. And you should go back through these steps for the 41.5 degree. Everything else is the same, mass of the car, the distance between the gates. The only thing that's going to change is the photogates. The photogates will have different times for A and B, and they should be shorter times because you're at a steeper ramp. We hypothesized that the acceleration rate would be higher at a steeper angle, and that the I think we hypothesized that friction would also change, but you wanted to see how it would change. So for your lab, make sure that in your theory section of your lab you talk about what weight is, what its two components are on an incline, what normal force is, what friction is, and you talk about how you can calculate acceleration down an inclined plane with these three methods. And in your conclusion, make sure you talk about how friction comes into play to change our results. You also need to, in your calculation section, have both sets of calculations for trial 1 at 10 degrees and trial 2 at 41.5 degrees. Nicely spelled out. Make sure you use subscripts and superscripts, and make sure the math looks nice and clean. It doesn't matter how many pages you use because it's electronics, so space things out so it looks neat. If you have any questions, please email me for any clarification.